Itxaso Ariza, who is Chief Technology Officer of Tokamak Energy.
Next. So Itxaso Ariza, good morning. I come from Oxfordshire, where Tokamak Energy is based. Tokamak Energy was actually spun out of UKAEA in 2009. At the time, UKAEA was hosting JET, which is a conventional tokamak, more like a donut shape. But as part of UKAEA's research into fusion, some researchers at UKAEA were investigating the benefits of spherical tokamak, and with the promises that that research showed, they decided to set up their own company to pursue nuclear fusion with the concept of a spherical tokamak. Since then, the company has grown to employ about 300 people. We're based in Milton Park. And today we are organized around 3 different divisions. A fusion division on the left, which is centered around ST40, the latest and greatest of our nuclear fusion research devices, ST40. A T magnetics division, which is a division that I'll speak a bit more about later, which is aimed at commercializing products based on high temperature superconductors. Again, you will hear a bit more about those materials later in the presentation. And the third division is Ridgeway Machines. Ridgeway Machines was a strategic acquisition we made last year. It's a small company based in Leicester with over 100 years history, developing, manufacturing, delivering, and exporting mostly high precision machines for the manufacture of wiring, oil delivery lines in the Middle East, aerospace products, and more. As Lee said, we were selected earlier this year as magnet system partner for the government's STEP Fusion program. That is because of our HCS expertise, which we have developed in the last 10, 12 years. I cannot show you the video. It should activate on its own. I'm going to talk about the fusion division first. As said, the company started with an aim to develop fusion. This is an image of plasma in ST40. Through the last 15, 16 years, we have built a few research devices in Oxfordshire, and the latest is ST40. 40 refers to the distance between the center column and the center of the plasma, and that's 40 centimeters. So it's a really tiny device. But today, as we speak, it's the spherical tokamak with the highest field that is in operation today in private hands. And we use it to do nuclear fusion research in an agile and, let's say, flexible way. In 2022, it achieved a plasma temperature of 100 million degrees centigrade in a really tiny device in Oxford. On a daily basis, it probably achieves 40, 50 million degrees temperature, plasma temperature. But perhaps for those who are not that familiar with fusion, the plasma temperature has got nothing to do with the temperature of the materials around it. And actually, in our case, and especially with the magnets, it is actually cryogenic temperatures that we need to worry about. Thank you for the video playing. So in our fusion division, we have developed different technologies. We are at the moment upgrading ST40 to fit a gyrotron. Helen will speak more about gyrotrons later, but it is basically a heating device to get the plasma to the temperatures you need to get it to achieve commercial fusion. It is an electron cyclotron resonance heating device. The plasma needs to get very hot and under a lot of pressure to achieve fusion. Fusion is obviously the reaction that hits the sun and the reaction that happens in the sun on a daily basis, on a continuous basis. But in the sun, you have gravity to help you. And we don't have the enormous gravity that the sun has on Earth, so we use magnets. There are different ways to achieve fusion. STEP is a spherical tokamak, magnetic confinement fusion. ST40 is a spherical tokamak. JET was a tokamak. The Stellarator that Proxima are going to build in Germany is also magnetic confinement fusion, and you have other types of magnetic confinement fusion. To achieve the pressures that compensate for the lack of the sun's gravity, you need really, really powerful magnetic fields. To date, the majority of those magnetic fields have been achieved with copper electromagnets, but copper, although it is one of the best materials we can use to transmit or transport current, it offers some resistance to the current and basically heats. So when you're trying to achieve a really high magnetic field, you need to pass on a lot of current through those magnets, and basically they overheat because they cannot take that much current. And you cannot achieve the magnetic fields that are required for a step with copper electromagnets. That led a few very forward-looking scientists to take a technology that was known about in the 1970s, which was superconductors, and try and develop electromagnets based on that material, because superconductors achieve or offer zero resistance to current when they are cooled down sufficiently. So basically that barrier to the amount of amperes you can take through the electromagnet is completely removed in this case. I'm going to talk a bit more about HTS in the next slide, but basically it is the foundational technology for anybody trying to do magnetic confinement fusion in the future. HTS, the game changer. Superconducting materials need to be cooled down to cryogenic temperatures to offer zero resistance to current. Today, you actually probably all have seen a superconductor in operation. If you are unlucky enough to have had to go under an MRI scan in the past. MRI scans use LTS, low temperature superconductors. They are materials, again, that offer zero resistance to current, but only when cooled down to 4 degrees Kelvin. So MRI scans, NMR machines, nuclear magnetic resonance machines in hospitals and research facilities use superconductors today. However, the temperature at which they are superconducting is so narrow that they are not very practical. They need liquid helium to cool them down, which comes with safety challenges, infrastructure challenges, and also supply challenges. The biggest supplier of liquid helium happens to be in the Middle East and was bombed only a couple of months ago in the war. So the price of liquid helium is increasing, the scarcity of liquid helium, and actually the consequences or the implications of having liquid helium cooling has actually limited the applicability of LTS superconductors in the world. But what if I told you that there are high temperature superconductors which still need to be cooled down to 20 Kelvin, so it's high in relation to the low temperature superconductors, but actually it offers a much more practical applicability of this technology. These materials are not new. They have been known about, like I say, for decades. What is new is the ability to manufacture a tape based on a very tiny amount of these superconductors, so that then you can actually make things with these materials. You don't have to just look at them in a microscope, under a microscope in a lab. When you use HTS, because of the increased temperature, you can use liquid nitrogen to cool it down to 77 Kelvin, or gaseous helium, which again is a bit like a cryogenic cooler, which is a lot more compatible with widespread application. On the left-hand side, you have not to scale of what the HTS tape looks like. I have one in my bag. I forgot to bring it out, but it's really 70 micron thick tape, out of which only 1 to 3 microns is a superconductor. But that very thin tape can carry thousands of ampere. It's a really, really thin tape, but 1,000 ampere per tape. And you can put as many as you want, one on top of the other, to carry multiple kiloampere. If you compare that to the cabling in your house, limited to 13 ampere. So basically, the opportunities of this superconductivity are significant. It does contain some copper and hastelloy and all the materials for resistance and for maneuverability and manufacturability. But with that tape, you can make almost anything that you want to have for either transmitting power in high density applications, or where you want a very powerful compact magnet. Fusion is the industry that needed superconductors to be developed, and therefore went in and started to develop this technology, but actually the applications are vast. In recent years, we have seen the applications and the inquiries about superconductivity developing and increasing. Fusion energy, yes, is the first sector that basically drove the development of HTS. But science and medicine, I talked about MRI machines and NMR machines. Imagine a world where every hospital doesn't have 1 or 2 MRI machines, but it has 20 or 30 because they are cheaper and easier to implement, to set base. Or a world where every single laboratory can have 2 or 3 NMR machines in a lab. Today, if you want to have an NMR machine and mostly are owned by pharmaceutical companies because of how expensive they are, you basically need a building for the NMR machine and a building for the cooling system. Imagine you could have 4, 5, 10 in a space like this. Democratizing research, democratizing protein analysis, medicine development, and diagnosis in medicine is one of the multiple applications that HTS has. If you move on to propulsion, magnetic levitation trains are one of the solutions to aviation's climate impact. Well, what if you could have more powerful and more compact magnets in those trains? The speed could increase. You could have more trains of those around the world. You could probably replace more routes that are currently used by other methods of transport. And moving to the right, aviation. HTS may well be the enabling technology that enables hybrid electric flight. We are actually collaborating with a lot of other aerospace companies, and we are currently making prototype magnets that would be used in that application, again, to decarbonize flight. More recent years, power distribution has been the market that has surprised us. We have all heard that AI is going to require a lot of energy and that data centers are basically behind the growth on the energy consumption around the world. What we haven't heard so much about until the last 2-3 years, when the likes of Microsoft, Nvidia and others have explained this, is that the power density required in data centers and some of the power consumption come from AI is coming because of the use of copper. Copper is offering resistance to current. It has significant efficiency losses when you try to implement high density applications. And it actually doesn't have the density of power that an AI data center of tomorrow needs. It is being tried to compensate with high voltages, which have got safety consequences. So really, power distribution and power transmission is likely going to be the next application and one of the biggest applications of HTS technologies. I always say that the world of tomorrow needs nuclear and, if I may say, probably nuclear fusion. But the world of today and in the near future, the world needs HTS to democratize science, democratize access to medicine, and to decarbonize different sectors. So that's why we created the division T Magnetics, the second division that we have. HTS has been developed and researched in tokamak energy since its inception because it was needed for fusion. But we have one of the biggest specialist team in HTS in the world, 70, probably more like 80 specialist people in HTS and the surrounding systems, a lot of patents. The thing that really we're passionate about is the creation of modular, simplified, scalable designs that are safe for their application in the world of tomorrow. We have gone from a technology or a material that was poorly understood and then made into tape to now, how can you make products out of HTS that can truly be made at scale? I'm really proud to say that not only do we have really clever people, but also they seek simplicity in everything they do. And the innovation for us is not only in understanding HTS, but also in understanding how you make products out of it that actually can be made by anyone. What we were missing here, though, was the industrialization and commercialization and scale-up expertise. So last year, we made a very strategic acquisition and we acquired Ridgeway Machines, which is based in Leicester. It's a small company and you probably have not heard about. You may have driven past it and not have realized that this company with over 100 years experience or record has become the world expert in precision winding machinery for the world of HTS and the world of fusion. Out of that 20 people company, about 80% of the products are exported, and And it's basically an example of how a small company that started outside of Fusion has actually been able to acquire a piece of the revenue and the big pie that Fusion and HTS have become without having to turn their back on the previous markets that they were operating in and taking that potential risk of whether Fusion will or not actually grow in the way that is predicted to. So if anybody here is thinking about whether you should go into HTS and Fusion, Ridgeway is the perfect example of a company that has doubled its revenues through Fusion and HTS without having to take too much risk on or turn its back on its previous customers. Thank you.